After Faraday was made of the Fellow of the Royal Society, the Prime Minister of the day asked what good this invention could be, and Faraday answered, "Why, Prime Minister? Someday you can tax it." Frequently referred but probably apocryphal quote. Let me get the numbers and the dates straight. On the November 10th, 1974, they are running at 3.12 giga electron volt, and what they saw on their computer screen was a sort of the real-time image that shows the events that they were collecting. So the screen would light up every now and again, indicating that something interesting had happened, and it was lighting up a little bit more frequently than their usual baseline. So it did look, indeed, like there was something there. When you are a practical physicist, you have to be careful. You are kind of flipping coins, right? It's quantum mechanics. There is some randomness associated with the production of the particles. You gather energy. It will produce anything that it can produce, but only with a sort of the statistical distribution. So, if you are tossing coins for a living and you toss 6 heads in a row, do you get excited and think that you've got an unusual coin? Well, not if you have been tossing coins thousands and thousands of times. Six in the row is not all that unusual, so they really had to check their data and run for a longer amount of time. They changed the beam energy a little bit. They went from 3.12 to 3.11, and now the count rate just started exploding. The display was like a fireworks display. Flash, flash, flash. Particles were just appearing like crazy. So they had found something. They changed the beam energy again from 3.11 to 3.104, right? They are honing in on something. And now it's just crazy, hundreds and hundreds of times the regular event rates. And here's where the two stories converge, because this particle that was being discovered at Stanford was exactly the same particle that some team had discovered months earlier at Brookhaven. Of course, there is no communication between two labs yet, because some team had been keeping a lid on his data in the hopes of putting it all together and making absolutely sure that it was right before he announced it. The climate at Stanford was very different. Stanford was really one of the archetypes of the kind of the modern sociology of the particle physics. Extremely open laboratory. Physicists there were highly collaborative. The team were international. Everybody is on the phone. It was the most expensive telephone bill in the Slack's history up to that date. They are calling all their physics buddies in Europe. Alright. And on the East Coast and throughout the whole world, telling them about what they had, and because they were very excited, it was obviously a big discovery, and I think this is more in keeping with the usual climate of scientific discovery in the particle physics today. This collaborative nature is in fact what created the World Wide Web. World Wide Web, not in 1974, but at a later time. CERN in Europe, that was in the European Center for Nuclear Research, which was kind of the European version of our big laboratories. They, along with the big American laboratories, really wanted to share data as rapidly and easily as possible. I remember as a particle physics postdoc using the World Wide Web before there were any commercial websites. All that you had on the web were physics laboratories where you could look up data and collect information pretty much on the fly. Wow. It just so happened, by sheer coincidence, Sam Tin was in an airplane on the day on his way to Stanford, because every year, maybe even a couple of times a year, physicists get together. It's kind of the working group to discuss what's going on to happen at the National Laboratory. It's kind of a business meeting, and Sam Tin was part of that collaboration. And so he was on his way for this regularly scheduled meeting when this discovery was happening at Stanford. Now, the graduate student and postdocs at Brookhaven start hearing telephone calls because everybody is talking about this thing. And they are just freaking out. I mean, imagine how you would feel if you've just spent the last several months of your life spending, 18 hours days collecting this data, thinking this is your big break, and now somebody else is going to scoop you. So they are all frantic. And how do you research something? He's on the airplane. There are no telephones on the airplane in those days, so they left a message for him at the TWA gate, so that when he got off the plane, he would get this message. He gets a message late in the evening and realizes, I think probably to his horror, that he's about to be scooped. So he goes to his hotel room, and he hasn't even gone to Slack yet. He doesn't really know any of the details, and he starts making telephone calls himself, which he probably should have done much earlier. I don't want to criticize something. He's a great physicist, and he had in fact made the discovery first, and it was well analyzed and ready for publication by this point. But in any case, he made a telephone call to his colleagues at Brookhaven and at MIT, and really wanted to make it clear that this discovery was his. And the story goes that the next day, Sam Tin walks into the Burton Richter office, and Sam Tin says, Bert, I have some interesting physics to tell you about. And Bert says, Sam, I have something interesting physics to tell you about. And so they are, of course, each sharing the same physics, and they are both incredibly excited about it. Both of these papers ended up getting submitted to the journal at the same time, and they were published back to back, and a few years later they shared the Nobel Prize, Sam Tin and Bert Richter. It's sort of interesting to hear all this kind of the human aspect, which is always present, and the physics story often kind of misses out on this interesting character stuff. There is one more element to the human nature of this story. If you discover a particle, you get to name it, and it's kind of the big deal for a physicist. So Sam Tin wanted to name a particle as a J. Now, that's not the usual convention. People usually use the Greek letters for new particles, but J, it turns out, is very close to the Chinese character for his name. Wow. And he's a physicist, like many physicists, kind of the big ego, maybe, and so that's what he wanted to call it. That's what his name had been calling it. At Stanford, they had been calling it the Pussy, PSI, the Greek letter, Psycha. And it just so happens that PS are two of the letters in the name of their ring. It was called SPEAR, SPEAR, the Stanford Positional Electron Accelerator Ring. So they liked the name Psi particle, and so there was for many years some sort of the East Coast West Coast thing, where if you went to talk about this particle on the West Coast, it was Psi, and on the East Coast it was J nowadays. J nowadays. Really. course, the official name of this particle is J or psi. So that was the compromise. J slash psi. Why was this so exciting? Why is this a revolution in the physics? Well, you might just say, come on, it's another particle. You've just been telling me about, hundreds of particles that are produced. There wasn't something extraordinary special about J slash psi. First of all, its narrowness was a big surprise. The narrowest, the meaning it has an extremely definite energy, or if you're thinking quantum mechanically, it lives for a really long time. If you're thinking about Stanford experiment, E plus or E minus annihilate, you form a new little particle. You can figure out its quantum numbers. It has no electric charge, and you can figure out its spin. It's a boson, so it's a meson. It's a strongly interacting particle of the very high mass, 3 giga-electron-volt. You expect that it should decay immediately because all of the other particles in the zoo decay very, very rapidly. Alright. And the more massive they are, the more rapidly they decay. But this thing lived for really long time. Of course, it's still fractions of the second, but in the particle physics world, that's a forever. It's practically stable, so what is going on? This is a meson like no one has ever seen before, and there was a sort of a buzz in the physics community. But almost immediately, people figure out what this thing was. In fact, some people had predicted what it was before it was even seen. Let me tell you about 2 predictions that had been made in years before. First of all, I want you to think about the quarks that we talk about. There is an up quark and down quark. They are both quite similar. They are both quite light and they make up most of the ordinary world. One of them, the up quark has a charge 2/3. The down quark has a charge -1/3. So if you are imagining a little table, you've got an up quark and down quark next to each other. And then there is a heavier version of the down quark. It's also got a charge -1/3, just like the down quark. That's a strange quark. It's just like a down quark, only heavier and unstable. So there is this sort of the funny pattern. You've got 2 light quarks and only 1 heavy quark. So if you want to believe in the symmetry, you ask yourself, well, how come there is not a heavy partner to the up quark? How come there is not heavier version of the quark with a charge 2/3? And right away in 1964, people had thought about that. As soon as 3 quarks had been proposed, Sherry Glashow and James Bjorken were the physicists who published a paper in 1964 suggesting that maybe this would exist. And in fact, they thought it would be very charming if such a particle existed, because it would some sort of make the picture so elegant. So they called it the charm quark. Charm quark. You've got the strange quark, now you've got a charm quark. It's the 60s, people are being a little bit silly in their naming conventions. It was a nice idea, but shoot, people hardly even believe in quarks in those years. It's so speculative, and now you are speculating about the quarks that nobody is even seen or has any evidence for whatsoever, based on the theoretical symmetry grounds. So I think the idea was out there, but not really very well accepted. As the years went by, there were stronger arguments made for the existence of the charm quark. Glashow, again the same Glashow who had proposed the charm quark in the first place, along with a fellow named Iliopoulos and a fellow named Maiani, and these names are hard to pronounce. So people refer to the three of them as GIM or GIM, G-I-M or GIM. The GIM paper or the GIM mechanism was kind of a subtle theoretical argument. They were looking at some events in the bubble chambers that were not occurring, but everybody thought they should. You have a kaon particle and it can decay, and it decays in many different pathways. It might turn into a pion, it might turn into an electron. There is all sorts of the possibilities for how the kaon might decay, and one of those pathways didn't occur. So you have a kaon particle and it can decay, and it decays in many different pathways. It might turn into a pion, it might turn into an electron. There is all sorts of possibilities for how the kaon might decay, and one of those pathways didn't occur. It should be as there was no violation of any obvious conservation law, and Glashow, Iliopoulos, and Maiani came up with the explanation. It involved, during the Feynman diagrams, you have to draw every possible Feynman diagram and add them up before you know the probability for some event. And if you include virtual charm quarks, if you imagine creating a charm quark and then having it disappear again very quickly, it turns out mechanically that they would cancel all the other Feynman diagrams and you would get 0 as your final answer. So that would explain why you are getting no such events. Very esoteric. At that time, it actually pins down the mass of the mathematics of the charm quark. In order for the mass to work out, you would have to predict a certain particular mass for this charm quark. And sure enough, in retrospect, after the J psi particle was found, the mass of the J psi was exactly twice of the predicted mass of the charm quark. Wow. So what's the J psi particle? It's a anti-charm meson. It's a new meson which is built out of this brand new quark. The fourth quark, the charm quark, and its anti-quark. Now you've got a charm and anti-charm. So in the starting cases, this object doesn't have net charm. We call it naked. We call it hidden charm. Naked charm would be if you produced a meson that was a charm and anti-up, or a charm and anti-down, or you could have naked naked charm in a baryon if you produced, for example, a charm up, or a charm down, up, or any of the quarks or combination that you could imagine involving the charm. So now a whole industry begins in the particle accelerators. Let's go look for all these new possible things that you can see in the laboratory, the new mesons and the new baryons, and they were all found. So you have to appreciate the significance of the J psi. It's a new quark, so that's exciting. And I think in a certain sense, the reality of these quarks, the fact that all the new particles appeared just as the expected form, expected from the quark model, really clinched the idea of quarks. So, in this November Revolution, it wasn't that it was a completely new idea. The idea had been all around, but what was really exciting and radical and transformational in the physics community was that all of a sudden the idea of quarks went from the sort of an abstract and slightly radical proposition to the pretty much a mainstream, well-established, almost orthodox philosophy. I think the discovery of the J psi was a big critical event in making us really believe in the physical reality of quarks. Wow.